Welcome to our presentation, Dr. Hazaruddin. We are pleased to present our project on hashing technique. My name is Cheong Jian and my student ID is 301803. Joining me are my group mates Jun Wen, ID 292145, and Yong Jia Hao, ID 293740. Together, we've explored and implemented three key hashing methods in Java, with a focus on how they handle collisions and perform under different conditions. Let's begin by walking you through the core idea behind the project. This project dwells into the core of one of the most efficient data access strategies in computer science, hashing. At its essence, hashing is a method to map data to fixed size storage using hash functions, optimizing retrieval time to a near constant big O notation of O1 in best case scenarios. Our implementation focuses on three foundational collision resolution strategies: open addressing with linear probing, as well as quadratic probing, and separate chaining. Developed in Java, the program dynamically accepts a prime size hash table and key inputs, then applies both techniques to demonstrate that distinct approaches to collision resolution. Through comparative visualization of the resulting tables, the project offers not only a hands-on view of hashing mechanics, but also insights into how different techniques behave under stress conditions such as clustering or high load factors. Ultimately, this work bridges theoretical understanding and practical application, the cornerstone of effective data structure mastery. Hashing leverages a mathematical function to translate a key into index within a bounded array, the hash table. However, the inevitability of collisions, where multiple keys map to the same index, necessitates robust resolution mechanisms. In this project, we implemented three: open addressing with linear probing, quadratic probing, and separate chaining. Linear probing searches linearly for the next empty slot in the event of a collision, cycling back to the beginning if needed. While space efficient, it suffers from primary clustering, where blocks of consecutive filled slots degrade performance over time. Quadratic probing refines this approach by using a quadratic function, typically probing at intervals of I squared for the ith attempt. For example, if the initial index is h, it checks h plus 1 squared, h plus 2 squared, h plus 3 squared, and so on. This reduces primary clustering, but may introduce secondary clustering, where keys with the same initial hash follow the same probe sequence. It's a balance between efficiency and spread, and unlike linear probing, it requires careful handling to avoid infinite loops, often demanding a load factor below 0.5 to guarantee insertions. Finally, separate chaining takes a different route by maintaining a linked list at each table index, allowing multiple keys to reside in the same slot. This sidesteps clustering altogether but increases memory usage and pointer overhead. By comparing all three, we illuminate trade-offs in space complexity, insertion speed, and performance under high load. Crucial in systems like databases, symbol tables, and cache implementations where collision management directly impacts throughput.
Good morning, doctor. My name is Yong Jia Hao, retrieval number 293740. Then I will present about 3.0, sample screen for all output. For insert input, firstly, we call the user to insert the size of hash table, which must be a prime number like 3, 7, 11, 13, and so on. If not, the user need to insert again until the number of size of hash table is a prime number. After insert the size of hash table, the user is called to insert a number of key, where the number of key cannot exceed the size of hash table. For return value, the key that are inserted will be returned to the respective index based on their value of remainder, where the remainder is equal to key over the size of hash table. In my case situation, I insert 7 for my size of hash table, 6 for my number of key, and my keys include 14, 66, 0, 25, 8, and 31. For open addressing, it divided into two parts. One is linear probing and other one is quadratic probing. And for linear probing, each index can store only one element, and collisions are resolved by probing to the next available index. We can observe that the key 14, 66, 25 are inserted into their respective index based on the remainder without collisions, while key 0 had a collision at the index 0, so it need to move to the index 1, and key 8 had a collision at index 1, so it need to move to the index 2, and key 31 need to move to the index 5 due to the collision at index 3 and 4. For open addressing using quadratic probing, each index can only store one element, where same with the linear probing. When the collision occurs, the algorithm will resolve it by probing the quadratically. We can observe that key 14, 66, 25 are inserted into their respective index based on the remainder, while key 0 had a collision at index 0, and based on the formula, it need to move to the index 1, and key 8 had a collision at index 1. Based on the formula, it need to move to the index 2, while key 31 had multiple collisions. Finally, it need to insert to the index 5 due to the collision at index 3, 4, and 0. For separate chaining, each index in the hash table can be stored in a linked list or a change of element that hash to the same index, and collisions are allowed in the same index, and the element can be inserted to the same index, and all elements are inserted into their respective index based on the remainder, and the collision occur but resolve within the same index using chaining.
In conclusion, this project did more than just implement three hashing techniques. It provided a comparative framework to evaluate the real-world behavior under practical conditions. Linear probing excels in memory-constrained environments due to its in-place storage, but suffers from primary clustering, especially as the load factor increases. Quadratic probing, by introducing non-linear probed sequences, mitigates primary clustering and offers better distribution of entries. However, it introduces secondary clustering and requires careful table sizing to ensure insertions are always possible. Separate chaining, while more memory intensive, offers consistent performance under high collision scenarios by decoupling keys through linked lists, avoiding clustering entirely. Through hands-on simulation in Java and testing with varying inputs and table sizes, we gain a deeper understanding of how each method responds to different stresses. This experience highlighted the importance of context-driven design, balancing speed, space, and reliability based on system requirements. More than code, it sharpened our data structure intuition and equipped us with tools essential for building efficient, scalable systems in the real world.
Good morning, Doctor. My name is Jun Wen, number metric 292145. Today, I would like to present the source code of our project. Our project is for hashing program. So first, we need to import the necessary file used for our project, like import the scanner class to read user output, and import the array field to fill the array, and import the linked list if we use in separate chaining. Then for hashing program, first we need to determine our hash function. This hash function will handle integer key. So this is the code for our hash function, which is key divide by table size. The integer is the remainder. Okay, now we'll move to the method one, open addressing, and we use linear probing. So first, we need to print a header for the open addressing linear probing to to guide the user, and we need to initialize the hash table for open addressing. So this is the code for the initialize. Then we use array.fill table -1, auto filling all slot of new created table array with -1. Then in this case, -1 means empty slot. So next, we use for function to calculate the initial hash index. we call hash function to calculate the initial index for the key. And we save the original one used to check if the hash table is full. So the next is counter. So next, we print the insertion information, use system out print line, inserting key. Okay, so this will show the insertion process. Then linear probing loop handling collision. So we use while function. As long as the current slot is not empty, -1, it indicates a collision. So we system out print line collision at index blah blah blah. So print collision information. Then next index is negative equal to negative index plus 1 table size and linear probing. Try the next lot, use the modulus to ensure index stay within the table bound. So next we use step plus plus to increase the probing step counter. Then next, we want to avoid the infinite loops when the table is full. So we use if function. If probing hash back to original index, means the hash table is full. So we need to print the information like hash function is full. So now cannot insert any key. Then we break to assist the loops as insertion is not possible. Okay, next, I'd like to present the method 2 open addressing quadratic probing. First, we need to print a header for the quadratic probing section to guide the user. Then we initialize the hash table for quadratic probing. Next, we will try inserting key with quadratic probing. Use while function if the table is full. So we need to print the information like collision at index. Index is full. So try next. Show the probing process. Then if we are try table size time, table is considered full. So use if function to print the information like hash table is full, cannot insert the key. Next, insert if a spot is found. So final, we display the final table. Okay. Okay, end of the method 1. Now we move to the method 2. Method 2 is separate chaining. So first, we need to print a header for the separate chaining section. Use system out print line to guide the user. Then declare and initialize the hash table as an array of linked lists. Each element in the array will hold a linked list to store key that hash to the same index. So this is the code for linked list. Then we initialize each chain linked list in the hash table array. Use for function, initialize each element with an empty linked list. Next, we insert the key into the hash table. Use for function, calculate the initial hash index for the current key. Then, for separate chaining, when a collision occurs, the key is simply added to the linked list at the calculated index. This is the core mechanism of separate chaining for resolving collision. Multiple keys can reside in the same element by forming a chain linked list. Then we print the insertion information to show the insertion process. Then finally we display the final table. Use system out print line. So this is end of the method 2. Then to ensure the user key in the table size with prime number, we need to do some function. Then this public static boolean is prime anti-num. If number is less or equal to 1, we return false. If number is equal to 2, we return true. If the number divide by 2, then the remainder equal to 0, we return false because this is not a prime number. Then for integer I equal to 3, we use the for function. If the number divided by n is equal to the remainder is equal to 0, then we return false because this is not a prime number. Else we return true. Okay, so for the user, for the next function, we use public static in get prime table size scanner. We initialize the size variable size first, then use a while function. While true system, we will print the information like enter the size of the hash table must be a prime number. Then size is for user key in, and if the first function is prime is break, so we print size must be a prime number. Then next we return size. Now I will move into the main method, entry point of the program. So first I will create a scanner object to read the input. Use scanner equals to new scanner system in. Then I will display a welcome header for the hashing program and get hash table size from the user, get number of key from the user, use scanner, then initialize an integer array to store the key based on the provided count. Next, get key from user. So ask user to enter the key, then loops to prompt the user for each key and store it in the key array. Use for function. Next, I will call the hashing method, three hashing method, which is linear proving, quadratic proving, and separate chaining. Then final, I will close the scanner to release the system resource. Scanner close. That's all from me. Thank you.